Welcome to the 15th lecture of graph theory. So, in the last class we were looking at the class of K-constructible graphs. So, to remind you what is a K-constructible graph. So, it is a graph which can be constructed using the following rules. The first rule is the complete graph on k vertices is a K-constructible graph. Now, if G is a K-constructible graph and x and y are two vertices which are non-adjacent in G, then you add that edge x y and contract after that. The resulting graph will also be K-constructible. The third rule is if G1 and G2 are two K-constructible graphs and there are vertices x, y1 and y2 such that the only common vertex of G1 and G2 is x, and the x y1 is an edge of G1 and x y2 is an edge of G2, then the union of G1 and G2 minus x y1 minus x y2 plus y1 y2 is K-constructible, which means we take these two things together and then delete those edges x y1 and x y2 and then add the new edge y1 y2. This will also be K-constructible. All graphs which can be constructed in this way is K-constructible. This is what yesterday we told, and also we argued that if a graph is K-constructible, then it needs k colors to color, its chromatic number is k. This is what we argued. What was the argument? So, for instance, the first rule there it is very clear, that means if it is a complete graph on k vertices, then it needs k colors to color, its chromatic number is k. And the second rule was also clear, because if the resulting graph after putting the edge and contracting it, right, x y edge x y were two new non-adjacent vertices, and we added that edge. So, we have this graph. So, x y were two non-adjacent vertices, we added that edge like this and then contracted it, right. So, if the resulting graph requires only less than k colors, of course it is easy to see that the original graph also requires the same number of colors, because the same color can be retained here. For instance, after contracting, suppose the graph is like this. So, this is the Vxy after contracting. So, whatever color you give, say red color, then the same red color can be given to both the vertices. Why? Because the originally this edge was not there, right, we just, and so the whichever neighbors were there, they were here also, right. So, the colors the neighbors get here will still be here. Now, this color can be given to both these vertices, because they will be different from the colors on the neighbors, right. Therefore, if after putting this edge and contracting the graph requires only less than k colors, then the original graph also can be colored with less than k colors. That will be a contradiction to the assumption that the original graph required more than or equal to k colors, right. So, so that the assumption that the original graph was K-constructible. Now, the third rule also was easy, because if the resulting graph, so we had this kind of a structure, this was the common vertex x. So, this was G1, which is assumed to be K-constructible, and therefore assumed to require k colors to vertex color. Now, what we did, we identified these two edges, right, and then so what we did is we decided to delete these edges from the graph, two edges, and then add this new edge, add this new edge. This was what we did, add this new edge. So, we can say this is a new edge, red colored. So, of course, if after doing this thing, if you could color the graph using less than k colors, what can we say? We can say that in that case we can definitely look at the color of y1 and y2. This because of this edge, at least one of them have a color which is different from that of x, and then say suppose y2 has different color from x, then naturally you can consider this part, and then if you put back this edge, it will not violate any condition because this and this have different colors. So, the same k less than k colors will suffice for this G2 also. That will be a contradiction because we assume that this is k constructible and requires more than or equal to k colors. This was the argument we did. Now, the other part of the statement says that if G the G such that the chromatic number of G is greater than or equal to k, then there exists a subgraph in G such that it is k constructible. This is what, right. So, let G be a graph and k element of n, then if chromatic number of this chromatic number of the graph is greater than or equal to k, if and only if G has a k constructible subgraph in it. How do you show this? To show this thing, so we will prove by contradiction. Suppose there is such a graph, that means this G is a k chromatic graph, that means it requires at least k colors to vertex color. Now, suppose none of its subgraphs is k constructible. Now, what we can do is we can add edges to the graph. So, when you add edges, the chromatic number will only go up, but we will keep adding edges as long as there is no k constructible subgraph in it, results in it. See, for instance, when you add one more edge, it is possible that many new subgraphs will come, and then one of these subgraphs may be k constructible, right. But if such a k constructible subgraph does not result by adding a new edge, you can add that edge. So, in that way we make the graph edge maximal. So, we are familiar with this word edge maximal with this property that none of its subgraphs are k constructible, right. We will come to a contradiction to this. This is not possible because see, we will say that you can say that if suppose there is a graph with chromatic number greater than or equal to k and with none of its subgraphs not k constructible, then we can indeed make it edge maximal with that property, namely keep on adding edges until it retains the property, as long as it retains the property that there is no k constructible subgraph of it. So, at some point of time any new edge you add, you will end up with a k constructible subgraph in it. So, in this stage we will show a contradiction. So, because so what do we do? So, we first we ask this question, is it possible that this graph G, this edge graph maximal graph G is a complete k-partite graph? Is it a complete k-partite graph? Is it possible? So, we claim that it is not a complete k-partite graph, because if it is a complete k-partite graph, then which for some k, I mean k-partite graph in the sense of some k, but then you know it is a complete k-partite graph means that k has to be at least the chromatic number. So, it should be at least k, right. So, complete, so you should say complete t-partite graph for some this thing. So, definitely t greater than or equal to k, right, because otherwise you can color it with t colors if t is less than k. So, the assumption that the G's chromatic number is k will be violated, right. So, but then if this is a complete k t-partite graph with t greater than or equal to k, then definitely you can consider the one vertex from each of this part, and then what will you get? You will get a complete graph on t vertices, that means complete graph on at least k vertices, in the graph, and that is indeed a K right. It is a complete graph on K vertices, indeed a K constructible subgraph of G, right. So, we can assume that it is not a complete K-partite graph. Then what can we tell? If it is not a complete K-partite graph, then we can immediately say that you look at the relation induced by the non-adjacency of vertices. See the relation defined on V cross V. So, by this rule that U and V belong to the relation if U is not adjacent to V, right. This relation is a it is, if it is an equivalence relation, what will happen? It will give you partitions, right. So, like this, and then such that none of them. So, this will essentially form a complete graph. So, when the underlying graph is not a complete K-partite graph, right. So, this relation of non-adjacency cannot be an equivalence relation. Why? Because an equivalence relation will give you equivalence classes. That means, if you take a class that none of them will be non-adjacent with each other. So, none of them they will be adjacent with each other, that means any pair among them will be non-adjacent. So, that is a class, and if you take any other vertex outside, you will not see that that pair is non-adjacent to this. That is why this complete connection comes, right. So, because we know that this is not the situation, so this cannot be an equivalence relation. So, why is it not an equivalence relation? So, if you remember, the properties for a graph to be for a relation to be an equivalence relation is this three thing: reflexive, well, that we can always assume A is there, right. It here also in any graph we can simply assume that, and then the second is the symmetry. If AB is there, BA is also there. Non-adjacency is such a relation, definitely it will be true. So, what will be violated then if it is not an equivalent? The third condition, namely the transitivity, will be violated. Why is transitivity violated? It's, see, it should be because there are some vertices in the graph, some y1 comma x element of the relation, right, some x y2 element of the relation, but some the y1 y2 is not element of the relation, right. This is why the transitivity is violated. There should be some pair x1 y1 x and x y2 element of the relation, but y1 y2 not element of. If it was transitive, y1 y2 would have been in the relation. So, if for every possible y1 x y2 pair, if this was y1 y2 also was element of R, then we would have told that it is a transitive relation along with reflexivity and symmetry. So, we would have told that it is an equivalence relation. But since we know that it is not an equivalence relation and the transitivity is not true, so we should be able to find some 3 vertices of this type. So, now so we have y1 x there, x y2 there, but y1 y2 is not there, which means that the y1 x is not in the edge set of the graph, and see x y2 is not in the edge set of the graph, and but y1 y2 is in the edge set of the graph, in the edge set of the graph. This is what it says, right, because the relation was non-adjacency. So, these two are y1 and x are non-adjacent, x and y2 are non-adjacent. So, y1 and x are y1 and y2 are adjacent. This is what we see, right. Such 3 vertices should be available. So, now if such 3 vertices are available, let us put it like this. So, suppose this is my x. So, we have x y1. So, this is non-adjacent, right, this is non-adjacent x y2 and this is adjacent. This is the way the graph is thing. See, the question is what will happen if I add this edge here. So, because of the edge assumption of edge maximality, because our graph was edge maximal with the property that there is no K-constructible subgraph in it. So, if you add one more edge, a K-constructible subgraph will come. For instance, if I add this edge, a K-constructible subgraph will immediately result in it, right. Let us say that K-constructible subgraph is H1, it contains this x y1 in it, right, because the newly added edge should be there. Otherwise, earlier also it was there, right. Similarly, suppose if I add this edge, you will get another subgraph H2 which contains x and y2 and which is a K-constructible subgraph. So, both this and this have to be K-constructible subgraph, they may share something, right. What we are going to do is to create a copy of, we will take H1, okay, x is there in it, while H2 we take only a copy, we do not use H2 as such from G. See, what we are going to do is we will take a copy of H2, but retain the original vertex x in it. So, it is a copy, but see, for instance, H can be somewhere here like this. So, we will take x, but then we will, for all other vertices in it, we will make a copy. Rather than taking the original vertices, we will just make a copy, right. And then okay, so right, so this is the thing. So, we will have H1 is as taken from the original graph G, and then here x I retain, H2 we will make a see H2 see, for instance, the vertices which were in H2 minus H1 I can take from G, right. So, as usual the original ones I can take, but those vertices which were shared we have to only make the copy of these things, because we want only x to be common to this. So, what will happen is here is a y1 now, so there is this edge. So, because this edge we have added, right. So, this edge we had added. So, now similarly this y2 is here. So, here we have our y2. So, similarly this edge we had added, remember, right. So, now what you see is two graphs H1 which is K-constructible, another graph H2 which is K-constructible. So, like we have, it is possible that in the original graph some of these vertices were common, but for instance, if this was u1, u2 etc., we will take a copy of that u1 dash, u2 dash, u3 dash, so that this will not share anything with this other than x, that is the intention, right. So, we want only x to be common to both of them. Now, we know this is like our original construction. What we do is we just delete these two edges, third rule of the K-constructibility. So, we will add this one instead, sorry, this will, we will add this edge like the third one. After deleting this xy1 and xy2, we will add this 2. Remember this y2 edge was there in the original graph. So, because we have copies here, therefore, we can add this one, right. So, it will be an edge of the original graph only. And now what you do, so whichever was common vertices here, we should see you see that this graph, because it is constructed from two K-constructible graphs by the third rule, it is again K-constructible. Now, we can identify two vertices which are as such non-adjacent here, but actually copies of the original thing. So, now what you can do is you can try to identify these vertices, corresponding vertices here, the same vertices, and then if you identify here and then here like that. So, it is like merging them together, and you will definitely get the original graph G, right. So, and this each of this merging correspond to the second rule, right, because whenever two non-adjacent vertices are identified and then you put the edge and contract them, that means they identify those two vertices, two non adjacent vertices, the same neighbors. So, because the neighbors slowly all the neighbors will get merged. So, therefore, in the graph, so it will this, if you only the original neighbors which were there in the G, okay, minus, because we are only taking a subgraph of it, some vertices will not come, but so we will get a subgraph of G by this merging process. So, that because we applied the second rule to an already K-constructible graph, so we end up getting a K-constructible graph. So, what have we proved now? We have shown that any K chromatic graph, if the chromatic number of the graph is at least K, then it contains a K constructible subgraph in it. This is what we have shown. This is a result of Hajos. So, now so the key point is, so to identify some structure in a K chromatic graph. So, if the coloring, so some subgraph which causes the chromatic number to be high, this is the intention. So, but if you ask a novice, a beginner, to this question, why is the chromatic number high, it is very likely that he may be misled to tell that it is because of some large cliques in the graph. So, it is the initial intuition probably to believe that when there are large cliques in the graph, so of course, when there are large cliques in the graph, the chromatic number is high. So, one may even in the beginning one may think that it is because of the large cliques that the chromatic number is high. It is not true, because even in graphs where the clique number, that means the maximum clique size is as small as 2, that means not even a triangle is available, not even a K3 is available, then also your chromatic number can be arbitrarily large, it can be as large as possible, right. So, for instance, we can make this statement, given a positive integer K, we can construct a triangle free graph with chromatic number greater than or equal to K. So, initially it may look like a little contradictory. So, for instance, if it is one vertex, it is very trivial, and also if two vertices you can just take an edge, there is no triangle in it, its chromatic number is 2, K equal to 2, K equal to 1 case, K equal to 2 case, K equal to 3 case, you cannot take this is a triangle, right. This is not the one we are looking for. So, but this one will do, this is a pentagon, a vertex on 5 vertices, a cycle on 5 vertices. This will create, this will allow us to see this is essentially a triangle free graph which requires 3 colors to color it, right. So, chromatic number is equal to 3, but there is no triangle in it. Now, the way to construct a graph. So, one way to construct a graph without triangle and having K plus 1 chromatic number is equal to K plus 1 or greater than equal to K plus 1 is to take one graph, say for instance a pentagon, if you take the chromatic number is 3, or in general a chromatic number equal to K graph, right, and then you just, this is 1 2 3 4 5 the vertices, you just make copies 1 dash 2 dash 3 dash 4 dash and 5 dash, and then we have to connect to the neighbors of it like this, right. So, this is this construction will give us a graph for 1 dash 2, for instance, you can put it 1 and 3, 3 you can put 2 and 4, and 4 you can put 5 and 3. So, for 5 dash you can put its neighbors. This is what we So, if you construct and then if you put one vertex here and this, in general what you do is you can make a k vertices here and the copies of k vertices here and then one more vertex if you add, then you can create a graph without it is very easy to check that there is no triangle in it, and then you can also argue that so you do not have your chromatic number will be more than k. So, you start with a k chromatic graph without a triangle here, and then for suppose there are n vertices, you make copies of n vertices here. Each vertex will be made adjacent to the neighbors of its corresponding vertex in the original graph, and then finally we will add one vertex the last, and then it will connect, it is connected to all of them. You can argue that this requires k plus 1 colors because the original one required k colors, right, and also it is very easy to show that it is triangle free. So this is the way to show that in fact we can construct triangle free graphs without so triangle free graphs with chromatic number at least k. So, I will move on to a new topic, namely edge coloring. So, the edge coloring, like vertex coloring, is the problem of coloring the edges of a graph in such a way that two adjacent edges get different colors. So, for instance, if this is the graph, how do you edge color it? So, you may want to use green color for this, red color for this, maybe a black color for this. So, now these three are, so red, black, yellow here. Here is edge colored. Here what should I do? I can use for instance yellow color here, and then can I use the same black color here? No, you may have to use a different color here. I use three colors. So, yeah, one possibility was to, yeah, so if I want to reduce the number of colors, what I should do is I should use green color for this thing, I should use black color for this thing. So, then I end up coloring, right, so this way. So, this is what green color and black color will do. Right. Now, see so let us see some examples. For instance, what will be a very natural and easy lower bound for the edge chromatic index? What do I mean by edge chromatic index? It is the minimum number of colors required to edge color the graph properly. Properly means any two edges which are adjacent, which are incident on some same vertex, on the same vertex. So, like this, right, they should get different colors, right, that is only condition. For instance, the most natural upper bound for edge coloring, if you think for some time, is this. For instance, if there are so many edges incident on the same vertex, they cannot share colors, right, they should get all different colors. So, it is not possible to give a red here and again a red here, right, that will be a violation. So, if I can only give different colors to these things, right, you cannot repeat colors, yeah, you cannot repeat colors, right. So, this should be the way it is colored. So, then the question is, so what will be the biggest upper bound I can get by this argument? Naturally, it is the maximum degree delta. For instance, if I consider this parameter delta, the maximum degree, the biggest of the degrees among the vertices, so that will be a natural lower bound for the chromatic index of G. Now the most interesting result here about edge coloring would be this. So if you consider the chromatic index of a graph, that means the number of colors required to edge color the graph, it is at least delta. It's also known that it's at most delta plus 1. So this is called the Voicings theorem. So this is about proper edge coloring. So the definition of the proper edge coloring I have told, and then Voicings theorem we will prove Voicings theorem in the next after proving one special case of it, namely the bipartite case. So the bipartite case says if it is a bipartite graph, this lower bound, this obvious lower bound of delta is the actual value of the chromatic index of the graph. Essentially it requires only delta colors. That is what for bipartite graph it so happens. But so in general some graphs may require delta plus 1. Can you see some examples? For instance, some simple cases when we consider the odd cycles, for instance our pentagon, right? It requires 3 colors, isn't it? 1, 2. So if I start coloring like this, so here I will need a new color, right? 1, 2, 3 will be required, 3 colors, but delta equal to 2 only, right? So so there are some examples where you need one more color, but no example will be there which requires more than one color, is what Vizing says, if it is a simple graph. So but before moving to that, because it requires a little more sophisticated argument, we will take the very simple case of bipartite graph, and we will show that in fact in the case of bipartite graphs only delta colors are required. But how do we show this thing? Suppose you consider a delta coloring. So this is a bipartite graph. We will show by induction on the number of edges as usual. If there are no edges, there is nothing to prove. Delta equal to 0, we don't need any colors, so delta colors are enough. So suppose for m less than m edges we have proved. Suppose now I consider a graph with m edges, so the maximum degree is delta here. So you can pick up a vertex and delete an edge. This is x, y. So you know the original degree was at most delta, here x and y, right? Now what you do is, so you deleted an edge. So now how many edges are present here in both cases? So d of x now in g minus e, right? So d of x is less than equal to delta minus 1, and d of y is also less than equal to delta minus 1, right? 1 less. So it may be just exactly delta minus 1. Now how? So by induction we know that it can be colored using delta colors, right? So if it so happens that the delta itself reduced, then we are done, because anyway we are allowed to use one more color, we can use that new color. So we can assume that delta is not reduced. So this is colored using the delta colors are used, right? Now the point here is to consider, first we will see whether I can give a new color to this edge, this removed edge, from without any conflict. Where does the conflict arise? So for instance, when I try to give a green color to this, what will be preventing me from giving green color to this is if some green color is already here with respect to our coloring we got by induction, right? So this may be possible, right? So but we know that only delta minus 1 colors are used here, because only delta minus 1 edges are edges and after this removal. So, one color is available extra, one extra color is available. So, let us say this is alpha, alpha is available. I can try to give this alpha color to color alpha, maybe let me call, we can give the yellow color. So, I can try to give yellow color to this, but then the issue is the yellow color may not be the color which is missing here, yellow color may be here. So, then it will conflict on the other side, that means X allows yellow color to be given to this edge, but Y may not allow, right. So, Y may say that the only color which is missing in its neighborhood, on its edge set, I mean incident edges, is say blue color, right. It is possible that it may allow only blue color. So, here, so maybe I can take blue color, the missing color. So, blue is missing here, and then yellow is missing here, right. So, what we can try to do now is somehow make both the missing colors at x and y the same. If the missing colors at x and y are same, then we can use that color to color x y, right, because then there will not be any conflict, x also will be happy, y also will be happy. So, but why, how can I do that? So, what one strategy is to try out, see because this blue is available here. If blue was missing here, I could have colored with blue, this xy edge could have been colored with blue, right. So, see blue may be here. So, now see I will do like this. So, this is the big graph. So, now x is here, remember this is a bipartite graph, right. So, I know that blue is here. So, yellow is available here, right. Now, what I do is I trace the blue yellow track here. For instance, when I start with a blue edge, so then I can, at this vertex I can look for a yellow edge. So, how many edges, yellow edges? Only one yellow edge can be there if at all, otherwise it will stop. So, yellow edge. So, then it will take, then in this point I can again start look for a blue edge. So, is it possible that it will come back to some of the already visited vertices? No, it is not possible, because every vertex have one yellow edge and one blue edge, and here x does not have a yellow edge, it is not possible to come back. So, it will keep going, at some point where will it stop? Suppose it stopped here somewhere, suppose it stopped here. Now, what we can do is we can do an exchange of colors. So, for instance, all the in this path I can make this blue edges yellow and yellow edges blue. So, let us do that. For instance, I will make this yellow, and then of course there is a conflict here, the only conflict is here, then I will make this blue, right. Then of course I can make this yellow, and then I can make this blue. So, there will not be any conflict after this thing. We just switch the colors in this path, no other, because if there are some other edge here, it will be red or green or something, right, green, red, or whatever other color, but they will not have any problem whether it is yellow or blue, as long as they see different colors, it is okay for them. The only, when I change from yellow to blue, the only edge that is likely to complain is the blue edge, sorry, because blue will come, but then I am changing the blue to yellow also. So, therefore, there will not be any complaint, but the effect is that here now yellow is there, blue is missing here, right. Earlier blue was there, but this is missing now, blue is missing here also, it's missing here also. So, now I can use the blue edge to color this. So, that will settle without using any new color. I can give a color to that xy edge, right, isn't it. So, what do I conclude? So, it means that if I trace the blue yellow path, this was the blue yellow path, right. If I trace the blue yellow path, the original blue yellow path here, I will not abruptly stop anywhere. So, because if I stop somewhere other than y, then I can always do this exchanging yellow to blue and blue to yellow in that path, and then I will free blue from here, and then this will be I can color this XY edge. So what can happen is it can go all the way to the only thing that can happen is it will go all the way to y, it will go all the way to y, but how can it enter y? There is no blue edge at y, so it has to allow y through a yellow edge. So it has to enter through an yellow edge. This is the yellow edge. So and then there should be this blue edge, and there should be this yellow edge, sorry, yellow edge. So like that it will somehow enter there. So now what is the issue here? If suppose this happens, then our earlier strategy will not work. For instance, if you try to interchange yellow and blue here, so here of course yellow will come and blue will be freed from X side, but then y earlier y had a blue missing edge, but here instead of yellow, here instead of yellow we will have a blue now, and then y's missing edge will become yellow rather than blue. So that will not help us, because what was missing at X now is missing at Y, that is all. So they just interchange the role between X and Y, the colors, right. So that will not help us to resolve the issue. So if this happens, we are stuck, we cannot do the earlier thing. But then if you carefully look at it, this situation will never occur because of the following reason. Suppose if there is a path like this, start with the blue, yellow, blue, yellow, blue, yellow, and then when I am entering Y, it is a yellow edge. So how many edges I have used? Because I started with the blue, second is a yellow edge, third is a blue, fourth is a yellow edge. Therefore any yellow edge has to be an even number, right, at the second, fourth, sixth, like that. So therefore there will be an even number of edges in this path when I start from X and reaches Y. Now in the end, if I put this edge, if I try to add this edge, then what you get is an odd cycle, an even number of edges in the path and one this XY edge together is an odd cycle. But then a bipartite graph cannot have an odd cycle, because that is very easy to see. For instance, if this is a bipartite graph, so any cycle has to go once here, then come back here, then here, then here, then here. So if it is reaching back, it should be an even number of edges. It can never have an odd number of edges in its in a cycle in a bipartite graph, because it should zigzag from two sides, between two sides, and it should come back to the original site, right, where it started. So therefore we can immediately assume that this will never happen. So then what can happen? It will, if at all I trace the blue yellow edge, it should stop at some other vertex. So it cannot keep on going infinitely, right. So it should stop because it is a finite graph. It will stop at some point, and we will do with the exchange of blue and yellow, and by blue will be released at the X vertex. Blue was also missing at Y, and then that can be used to color the XY edge. Blue can be. So therefore we can extend the delta coloring of G minus E to G. This is why bipartite graphs can be delta colored. So this is the strategy. So now finally, so we will look at the Voicings theorem. So Voicings theorem says, okay, like of course bipartite graphs require only delta or delta plus 1 colors, while bipartite graphs require only delta colors, but in general it may require one more color. That is what Voicings color. But Voicings theorem says whatever it is, it will not require more than one color, just one extra color will be enough. So see so how will we prove that with at most delta plus 1 colors we can edge color any graph? So we will again do an induction on the number of edges. So to do this thing, so we will consider a simple observation. So we can, so as usual we consider a graph G, it is the maximum degree is delta. You can consider some edge, right. So you can remove that edge by induction assumption. So G minus E C is, say we can say X and Y is can be edge colored using at most delta plus 1 colors, right. See, because if the delta itself has reduced, then we are done, we will have an extra color to color. Therefore, we can assume that the delta did not reduce, the delta is same, the maximum degree is same. So, now, but now of course, there are, if you look at x, in fact, now delta minus 1 edges can be seen here like earlier. So, how many colors will be there around? Only delta minus 1, 2 colors are missing here, not 1. So, you can take, suppose some color is missing, some orange color is missing here, orange, sorry. So, maybe green color is missing here, the green color is missing at this thing, that means green color is not there for on any of this thing, and here let us say violet color is missing, violet is missing. Now, what will happen if I trace earlier, like earlier, if I trace the violet, suppose there is a violet here, right, and I trace the violet. If violet is missing here, violet is missing here and violet is also missing here, then we can easily give violet color to this. Suppose violet is here, and then I try to trace the violet green path here, right, violet green path here. So, is it possible that it can abruptly stop somewhere? So, if it abruptly stops somewhere, so then without reaching y, so then what we can do is, we can do the trick that we had done in the case of bipartite graph. We can just exchange the colors on this path, violet green, green will become violet and violet will become green, and then so the color will be released on this, right, violet. So, the green color will be, sorry, the here it will become green, and then violet color will be available for xy edge, because violet is missing at y also. So, what we can infer is, whenever we start a path like this, has to go all the way and reach y, right, reach y in the sense that so it can only enter through, violet is missing here, it can enter through only a green edge, and then some violet green path should, sorry, violet green path should, so it should be like this, right. So, in the bipartite case, we argued that it will never happen, because this is going to be an even path, sorry, violet, right, it is going to be an even path, and plus 1 edge will create an odd cycle. But if it is not a bipartite graph, that can happen, that can indeed happen. So, what we can just remember is, suppose if you have an edge, so G minus E, so if you x y, if you remove, and if you look at any coloring of G minus E, so if you cannot extend this coloring to G, then it is clear that if one color is missing at y and one color is missing at x, and if you trace the corresponding path, that should start from x and reach y, the whatever starting from x, it should reach y, right. So, otherwise we can do that exchange strategy along the path, and then we will release a color for the xy edge. This is the thing. Okay. Now, the next point is, suppose now I try to do the induction like this. Suppose you get one vertex x, right. Now, you can think that there is a y0 here, which I removed. So, this is the other neighbors of it, y1, y2, other neighbors of it, right. So, here I just decided to remove this edge, so that in the remaining graph we have a coloring, right. So, this coloring, say C0, that is the coloring of this thing. So, we can call this graph, after removing this edge, you can call this graph G0. So, this coloring C0 of G0 will be such that, so okay, if you look at the missing edge here, because there is a missing edge here, right, because delta plus 1 colors are there. So then two missing edges are there, we can just say one missing edge is here, and then the missing edge here will also be different, right. Now what we can do is, so we can see that here also there is a missing edge. Suppose green is missing here, right. See, among all these edges, right, so one of them may be green, right. So okay, so we can pick it up, right, and then we can consider, so we will rearrange the, so for instance this is a green edge, and then here there will be one color missing, right. So let us say some red color is missing here, the red color is missing here. So now what we do is, see, I look for the red edge here, suppose the red edge is here, suppose this, so something, so it may be possible that the red edge is here. So so this will be called y1 now, so I'll renumber this vertices y1 and this red edge, and this will be called y2, and then I'll see what color is missing here. Suppose violet color is missing, suppose violet may be here, right, violet may be here, so I'll call it y3 and onwards. So and then I'll base this, I'll make this order of this edges, the neighbors, and then say I can rearrange them. For instance, I can redraw the figure now like this. So this is x, this is y0, y1, this is y2 up to yk, and so on, right. The point is, whatever with respect to the original coloring, so for instance I may with respect to the original coloring, whatever color is missing here will be the color of this xy1 edge, right, and then whatever color is missing here will be the color of the y2, the edge xy2, and the whatever color is missing here will be the color of xy3, and so on. And this may not be possible, we may not be able to it may not be possible to extend this sequence till it covers all the neighbors, but say yk is such that now if you look at the missing edge, it is not present anywhere, right, it is not present anywhere. So therefore so in that case we can we will stop it, right, isn't it. So now this coloring, the original coloring is C0, and then this edge, when I remove the graph, will be called G0. Now what we do is, we can use the color on this for this edge, right. I can put back this edge, and whatever color is there for xy1 with respect to C0, I can give it to this and remove this edge, right. Why is it possible? Because this was the missing color for y0 was available here, and then x will not protest anyway, x had already this thing, I am only deleting this and giving it to this, right. So this new graph can be called G1, and the new coloring may be called C1. See, the C1 and C0 are only very slightly different, the coloring is more or less same, it is only just the exchange, all other edges will retain their coloring, right. Now the third one, so what we do is, we can give the color of this edge xy2 to here, and then remove this edge, then the new graph will be called G2, and the new coloring will be called C2, right. And similarly for y3. So like that, for each of these things I can create a new graph and GK, new graph and new coloring, right. So while these colorings can be seen as derived from the original coloring. These graphs and the coloring can be seen as related to the original graph like this. For instance, the original graph was G0 by the removed XY0H. So, G1 is the graph obtained by starting from G and then remove the XY1H. So, GYI sorry GI is the graph obtained by removing the XYIH, right. So, now similarly the coloring C0 was the coloring which you obtained by induction when I removed this edge XY0. So, but then the coloring of XY G1 which I named C1 is the coloring which I obtained by rotating this color, I mean giving this color to this and making this empty, right, deleting that edge. Similarly, C2 is a color obtained by giving this color to this color to this and making this empty, right. Similarly, G3 will be by a 3 level rotation, this color will go to this, the color of this will go to this and this will go to this. So, therefore, from C0 it can be obtained by 3 rotations, right, sorry 2 rotations of colors, right. So, like that we can think of C1, C2, C3 etc. as derived from C0 by some kind of rotating the colors on this thing. So, we will complete the proof in the next class. Thank you.